Welcome to this technology demonstration featuring Autodesk manufacturing technology at work. In this example, the design team has been challenged to increase throughput of this robotic welding station. Not only will their customer benefit from being able to produce more, the manufacturer could increase market share by offering better performing products and lower overall material and production costs through reduction of material used in the design. One significant difference you will see during this demonstration is the idea of predictive versus iterative design. Autodesk's shape generator technology enables engineers to define form based on the function that a component will perform. Let's have a look. One of the new Inventor Professional tools available is something truly revolutionary. It's called Shape Generator. This approach to design moves powerful analytic tools to the front of the design process, as opposed to traditional methods after the initial design concepts are created. This workflow enables users to drive initial design intelligently as a function of the physical constraints and loads the design is exposed to, as well as density, elastic modulus, and other properties of the material being used. Once the initial shape is defined, environment variables such as fixed, grounded, pin joints, or frictionless sliding constraints are added. Subsequently, loads such as forces, pressures, moments, or bearing loads can be applied. Preserved regions may exclude zones where material will not be removed. In this example, these are areas where the pivot joint, hydraulic cylinder, and clamp are mounted. Finally, a mass removal target is defined and the shape generator solver begins. This new technique promises to transform design productivity in ways not previously possible, as the initial model shape is defined primarily by the demands of the physical environment the part will operate in. This generative shape is then merged with the initial model volume, and then any one of a number of modeling techniques can be used to remove material from the volume, leaving the minimum amount of material required to match the results defined by Shape Generator. In this case, traditional sketched volumes are created and used to remove a bulk of the material that is not needed. Direct modeling and freeform tools may also be used, depending on the complexity of the part, and the shape of the areas that need to be removed. Fillets are added for blending purposes, and finally the part is saved, and checked into the vault with the rest of the new clamp assembly. The shape generator process was also used on the main clamp backplate. And here we used Inventor's replace component functionality to swap the new for the old. Finally, these changes are driven down to the assembly, and all existing instances are updated with the new configuration. With the new clamp design, it's time to make sure that it will last for the life of the ASIDEK welding fixture. We can do this right in the CAD design environment. We can even use boundary conditions from the Shape Generator study to save time and ensure consistency. In the browser, there is the bearing load from the actuator, as well as the two constraints simulating the pin and contact with the automotive component. The material also comes over automatically and can be used for the virtual test. We could run a linear static study and simply test for stress and displacement, but that's not going to be enough. We need to know if the clamp can withstand 300,000 load cycles. This requires fatigue calculations. There are numerous ways to constrain and specify the boundary conditions. In this model, we have a hole that can only rotate along its axis. We know that there is a fastener connecting the part to the hinge plate. With the use of rigid connectors, we can then have full control over the geometry. Turn on and off the ability to move or rotate in any of the 6 degrees of freedom to simulate a pin or spherical constraint. Let's also make a change to the load. Fatigue results are based on the behavior of the actuator force on the clamp. Is it loaded and unloaded? Does the load reverse in the other direction? The actuator in this case only applies the load in one direction. These load curves are fully customizable for any load condition. Finally, let's mesh the part or break it up into smaller pieces to be analyzed, and run the study, which only takes a few seconds to calculate on this component. Taking a look at stress, we can see the value is very low. Shape Generator did a great job of finding the best possible geometry for a lightweight component. We can also see the fatigue results show there is zero damage over the life of the part. Is it possible we can make it even lighter? Why not try different material types, even plastic? Nonlinear studies are extremely powerful. They provide high-fidelity results for all material types including plastics, rubber, foam, and more. Let's edit the material we used in the previous fatigue study and change it to UHMW. We will find out how much of the load it will handle before it yields or maybe even buckles. Nonlinear studies are highly accurate. We will spread the load out in 30 increments and observe the results as it is gradually applied. We will also increase the load to ensure our safety factor is at least 2. Unlike linear static studies, we can watch the behavior of the part as the load is applied. Watch as the stiffness of the model changes and may even cause the part to buckle. This is something you will also never find in linear static results. They will only tell you if the material is going to pass or yield. Find out more about your design with fatigue, nonlinear, vibration, and thermal heat transfer. All within the CAD design environment. Even check the displacement of the model while the analysis is running. We can see that the part does in fact buckle at 1600 newtons. This does not satisfy our requirement of 2 times the normal load condition. Animations of the results may help to understand the weak points in the design for changes that need to be made in the model. We know that the design becomes unstable at 1600 newtons. By watching the animations, we can make better informed decisions for improvements to the stiffness of the geometry. Based on these results, we can confidently move forward with the model using mild steel. Using these types of studies, we can fully understand our design and run several what-if scenarios with various materials. Now let's check the design in with a message for the rest of the engineering team. From here, the engineering change order can be approved and released to manufacturing. Autodesk provides the technology for simulation-driven modeling using Shape Generator. Also validate parts and assemblies at any point right in the context of the CAD design environment using robust solvers for various types of studies. And manage it all in a secure and collaborative environment. Autodesk is your trusted solution. It is the future of making things.